Okay, cool. I'll start. So, hello everyone. My name is Yu, and today I'm going to present a paper called Real-Time Neural Rationalization for Large Scenes. All information of this paper is already in the titles. It focuses on the task of large scene rendering, and the goal is to be real-time. The approach used is neural rationalization. And in today's agenda, I will first go over these papers. I'll briefly go over these papers, but feel free to ask me any questions during the presentation. And second part, I will briefly talk about the representations beyond the, we'll talk about explicit representation like a mesh and the points like Gaussian splattings. And first, talk about the task of large scene overview synthesis. So we have seen a lot of love work rendering results, but there are another specific task called like for example drone videos. UAV may fly like over several square kilometers of regions, and also in self-driving scenes, the vehicle may drive like thousands of meters, and such a big large scene is very hard to be modeled by the popular nerve-based approach. So existing large scene obviously synthesis methods are typically very slow. For example, the megaLoaf, they break the drone views into several blocks, use a LoF to model each of the blocks. And similarly, in the block-LoF or Unisim, they break the large urban driving scene into several street blocks. And they use a LoF to model each of the street blocks. But still, those approaches are typically very slow, even though they look realistic. And there are some LoF-based approach to aim at real-time renderings. For example, mobile LoF, preemptive tree, or Snug. But those approach typically only works in small object level scenes. They fail to extend to the large scenes. And in today's work, we are going to present a method called RAS, which is focused on large scene real-time renderings. The right is interactively visualization of urban driving scenes. So first, we'll talk about the scene representations. Okay. This okay. So first, I'll talk about the scene representations. Instead of using here we're using mesh. So people may ask, what does this mesh come from? For now, let's just assume it's given. There are many sources of mesh. We can use a method like a structure from motion. We can use a comet to reconstruct the mesh. We can also use LoF-based neural reconstruction method to reconstruct the mesh. But for now, let's just assume that we have a mesh given for the scene. And we will talk about different how the mesh will affect the quality of renderings. And given a mesh of the 3D scene, we can generate a UV mapping. So you can think of the UV mapping as squeeze the 3D mesh into a 2D plane, and we can find the map between each pixels in the UV versus the surface in the mesh. And this is to model the nearby regions. But there are also some regions like the sky, which is infinitely far away from the ego views. And we can model it like using something called a multi-skybox. This is motivated by a approach called a multi-plane images, MPI. And it's also very popular representations in traditional graphics. They typically use skybox to model the sky region. And similarly, for each skybox, there is a cube mapping to represent its texture informations. And these explicit representations can be integrated into the classic graphics-based rendering engines. And this rendering could be very fast because GPU is designed like 40 years ago, it's designed to do the rasterization. Instead, and recently people are using the GPU to do the computation like the CUDA, but in the hardware level, the GPU is used for rasterization and it's much faster than the computation of CUDA or any neural network operations. And that's the reason why it can be very fast. And here the UV neural feature map is a learnable features, so we can try learn from data, and that's the reason why it can be realistic because it can memorize the data we have. So this is the representations, and here is the overall pipelines. We have the representations using mesh and the skybox. This is the geometry representations. And at the bottom part is the texture representation, the appearance representations. We have a learnable UV feature map and also learnable feature map for the sky regions, skybox. And then we can rasterize. Basically, we project the mesh, the skybox into the image space, the skin space. So we can get a feature map. It's not an RGB per pixel, it's a feature per pixels based on the UV features here, all the features in the sky regions here. And we have, for the sky region, we have multi-layers of feature map because we have different skybox at this different distance to the center of the eagle. And then we have MLP. The MLP takes the feature per pixels and the view direction per pixel out the RGB per pixels. And similarly, we have RGB for the sky regions. And then we do compose. The compose process is very similar to the word rendering. Basically, we compose from the nearest layer to the farthest layer, and we get the final render images. This is the training procedures. The learnable parameters here is the UV features and the sky features, as well as the MLP shaders here. These are the learnable component for this approach. And the geometry here is not learnable, it's fixed.
Sorry, how do you get mesh?
Yeah, this is a good question. Now, here we assume mesh is provided, but there are many sources of mesh. For example, we can run neural reconstruction. We can run NURB on this approach, and then we can run matching cube to extract mesh. We can also run COMAP, structure from motion or text or any 3D reconstruction method to get a mesh. We will analyze how different quality of mesh will affect the final rendered qualities. And here we just assume mesh is given. Okay. And this is our approach. We achieve the best realism and speed trade-off. And compared to those NURB-based approach, we are much faster. And compared to those geometry-based methods, we are more realistic. And here is results. We can render such large urban driving scenes in more than 100 frames per second. But as you can see, there are still quite a few artifacts on the top of the skin because of the better geometry there. And here are more results on the urban driving scenes, which is rendering at more than 100 frames per second. And similarly, here is our drone views. We can render we can interactively rendering large drone view scenes. But as you can see, there are some holes. That's because the mesh we have holes. So our method is not able to intend those missing geometry. And yeah, here is another example of interactive visualization results. Yeah, to the best of our knowledge, our approach is the first that can interactively render such large scenes interactively with such high realism. And yeah, this is a briefly summary of this approach. So we combine the neural textures, learnable neural textures, under rasterization for realistic large scene renderings in real time. Yeah, and here are some very similar works. First, similar works is Mobile Earth. They share a similar idea of using explicit mesh and learnable textures, and then can can rasterize the features in the screen space, plus using MLP to get an image. The approach itself is similar, but this work is for CVPR 2023. But when we try to run in the urban driving scenes, it's too slow and it cannot be generalized. It cannot produce reasonable results because their design doesn't fit for very large scenes. And there are some other similar work following. For example, the UE for Love, which is almost exactly the same idea of using a mesh plus a feature map and the neural shader to get the realistic results. And as mentioned, our approach is not able to refine the geometry. There is another work called Love to Mesh. It can refine the geometry. The idea is to first train a love and then matching cube to get the mesh. And then using this find the mesh as an initialization to use differentiable rendering like NVDiff Rust to optimize the geometry and the texture joint. Yeah. So yeah, as Mimi asked, how we get a mesh, and there are many sources of mesh, and different kind of mesh may affect the qualities. So first operation we did is how the number of polygons will affect the quality of renderings. On the left, we have a mesh with 50,000 triangles. On the right, we have a mesh with 500 triangles. So even with lower costs, with lower number of triangles, with the cost quality of mesh, we can still get a very decent rendering results. The PSNI is slightly worse, but not too much worse. And here is another example. We run instant NGP on the data set and we extract the mesh. The mesh here, as you can see, is very noisy. Yeah, but still we can get a decent results. I think it's because the neural texture and the MLP can somewhat compensate these geometry artifacts and overfitting the data I have. And similarly, on the right, we have Unisim, and we get a much better mesh. And the rendering quality actually isn't too much different in terms of PSNR.
So do you also predict an alpha value or like an opacity?
So for the foreground, we don't have alpha mesh, but for the background skybox, we have alpha in order to compensate.
So, yeah, I was wondering how the like extra artifacts are invisible kind of.
I think there are still artifacts. It's not. It can't compensate all artifacts, but most of part.
Yeah.
Yeah, it can. And here is another example from Mobile Love. As you can see, the rendering quality on the right is very good. But when you move to a different views, you can see there is no geometry on the table at all. But still, it has good appearance on the right. That's the reason is that the view on the left is not in the training view. It's far away from training views. So they only learn to overfit the overfit may be a better. They learn to memorize in the training data, which is on the right. But the geometry is actually quite bad. Even the geometry is bad, they're still able to memorize in the images on the right. So maybe geometry isn't that critical, but definitely geometry is necessary. Otherwise, when we extrapolate to a different views, we can see severe artifacts. And here is some other indications. For example, we don't have power lines on the sky. So as a result, we can model those fine details, fine grained geometry here. And also because the geometry here is quite bad, we don't have, because the mesh we exported doesn't model this region well, so we get artifacts here. And another indication is that when we zoom in very close to the mesh surface, it will be very blurry because the neural, we don't have a multi-level details representations of the. Okay, so one second.
Wait.
Yeah, I have a question. Can you hear me?
Yeah, sure.
Yeah, so can you go back a slide?
Mm-hmm.
Yeah, these artifacts, why do you think these are happening?
I think it's related to, this is an image I take from mobile love, and during mobile love, they have multi-stage trainings. And I think in the second stage, they extract the geometry. And the geometry they extract is actually not good, but still they try to overfit the training images with this bad geometry.
Are you sure about that? Because it seems like it's like a near plane cutting in the viewer rather than
I think
the problem with the geometry.
I think I can open the mobile love interactive online
Because I
views.
did see these kind of artifacts before, but these are just, it seems like a near plane cutting rather than
Yeah, it's this example.
like a cutting plane. Yeah.
So you are saying
This is outside training. This is outside training distribution, so you cannot model that.
So I think it's not a real view clipping. As you can see, the geometry here. So it could be the clipping, but I'm more leaning toward there is actually no geometry, but I could be no. So for example, the table, this region table here is actually modeled by the texture here.
Yeah, I think it's the ambiguity.
Right. But yeah, but it could also be near clipping.
Cool. Yeah. Thank you.
Yeah, can you actually go back to the slide where you were comparing to mobile? Can you say again why you think that mobile learn is slower than learning?
Mobile learning is not slower than our methods. I'm just saying mobile learning, its approach cannot be applied to large scenes because it has a lot of specific design for the object level. For example, they have some grid initialization, and this initialization doesn't fit for the large outdoor scenes, which is very complicated and large scales.
Okay, thank you.
And so I will just continue. And beyond the mesh representations, there is another type of representation which becomes quite popular recently, which is called point-based representations. It can be, I think the first one called MPBJ, which is CVPR 2021. The MPBJ plus is 2022. The idea is that they represent the scene as a set of points. So they have n points. Each point has a location. Each point also has a features called descriptors for each point. And during rendering, they rasterize these points to the target views. So we get similarly get features, images of features per pixels. And then they use a CNN to render the final results. And the very recent work using points representation is called Gaussian splitting. So it extends the points rendering to be the sphere and also Gaussian spherical harmonics. So, and they also made quite a few improvements to improve the rendering speed. As a result, they can achieve real-time rendering and a very fast speed during training. So there are some applications using Gaussian splitting. For example, image to 3D, people are replacing the representations with the Gaussian splitting. And also, I'll show you examples. Here is a 0, 1, 2, 3. If using love as a representation, it will be quite slow. But if using Gaussian splitting, it will be much faster in terms of conversion. And in the bottom, there are other demos like image through 3D, single image reconstruction, and also text through 3D. Also demonstrating that using Gaussian superlighting is much faster and also more realistic. Yeah, so here is a very brief summary of different kind of geometry notations. The love, which is implicit notation, has been very popular recent years. It's easy to optimize, but it's slow, especially for large things. And it need to predefine a volume size. So it's very hard to model the real world things. And the second type is the work I have just showed called explicit mesh plus neural texture. It's very fast, but it's hard to learn the geometry. Actually, the geometry in the project I demonstrated, it cannot be changed. It cannot be optimized. And the third approach is explicit points plus features. It's very easy to learn and very fast. I think a geometry can also be optimized. But based on what I have observed, the Gaussian spread papers, their geometry sometimes is not as good sometimes, but I'm not saying their geometry cannot be, no, it's just based on my limited experience. Yeah. And that is the last slide of my presentation. Thanks.
Thank you.
Any questions?
Are you looking to expand the work to point-wise?
Yeah, I'm doing some point-based experience. I think that's quite interesting.
Yeah. Thank you. Okay, that was a great work by Yoon. Okay, let's move. Okay, let's move to the next presenter, which is Anna. Thanks.
Oh, thanks.
All right, so yeah, I guess I'm presenting the adaptive shells for efficient neural radiance. What's the word behind that? Field rendering. All right. So generally, I guess as a motivation, oh, these can these work?
Yeah. It is working.
All right. So generally, I guess the motivation is that neural representations are currently like the go-to way for novel view synthesis and scene reconstruction. And the volumetric framework formulation is especially useful for like what they call fuzzy object, but basically like thin structures, like some hairs or stuff like that. But there's one issue, especially that you require a lot of samples. You need to sample a lot of points along array, and this slows down rendering and stuff like that. So this paper was kind of actually, I guess it was concurrent work to Gaussian splatting. So it's kind of a similar problem that they're tackling in some sense. But essentially, they say that neural representations require many, many samples to train with and to optimize. And they really just want to present a solution of how to get rid of the number of samples, or how to reduce the number of samples you sample along array to increase rendering time. So how they do that is they have a method to get like an outer and inner mesh, and these are meshes that are kind of bounding your zero level sets of like an SDF, and then this defines really your sampling region. So you can extract this mesh, do fast ray intersections with these inner and outer meshes, and then you can get like a region in which you can sample, basically a bounded region in which you can sample. Okay, so that's generally the motivation. Here's what this looks like exactly. So you have this not an object, but a person, and you have an inner and outer mesh, and these are basically the ones used for the ray intersections. And how they find these inner and outer meshes, or how they find like really the width of this inner and outer mesh, is kind of decided by a kernel size. And you can see here is the visualization of the kernel size. So where the object is, or where the person is, just has its skin, you can imagine that you only need 1 or 2 samples to render that. So that's why you have a smaller kernel size. and where you have many samples, or you want like a wider shell, a wider distance between the two shells, you have a bigger kernel size. Okay, that was the high level idea. Are there any questions at this point? Okay, cool. So exactly what are they doing exactly? So instead of using like a regular nerve type formulation or like a density based formulation, I guess there's also a density here, but they're using SDFs instead of occupancy, I guess. So how this would work is that your neural network outputs usually this F, which is your SDF value, and your radiance, which is C. Then in regular news formulation, you basically have a formula to go from these SDF values to a density, and then this density is just used in like a rendering formula. It's I guess it's not that important here right now, but what's important more is that this formula to get the actual density depends on a parameter called S, and this is like a global parameter. How you can actually think of this S, I guess, is there's some transformation to go from like an SDF to like a density, and you can go about it kind of arbitrarily. You can assign like a higher SDF more density or a lower SDF like lower density and stuff like that. So really this S parameter is kind of deciding what your shape around the object itself is. So you can see that with an S equal to 1 divided by 1,000, the density is kind of more crowded around F, while for S equals 1 over 100, your density is much flatter. Okay, so but this in use, this parameter S, which you can think of as your kernel size, it's a global parameter. So it's like a hyperparameter they decide overall for all of the space. While what they want, because they have these like objects with both fuzzy regions and like just surface regions, they want this S to be decided per point. They want the S to be varying in space. So that's why they're also outputting an S value. So their neural network outputs both then radiance, the SDF value, and an S, which is like the kernel size or kernel width, whatever. Okay, then after that, they use like the same formulas and everything to go to like density. Okay, are there any questions on this one? Okay, so once they have like this SDF field, what they do is they use like dilation and erosion, and that's basically I won't go into the detail of this, but you have your 0 level set, and then you erode it so you can get like a smaller area, and then you dilate it so you get like a bigger area, and these two areas basically decide. They do this on like on a grid, and then they run marching cubes on that to extract the mesh. So that's how they extract the inner and outer shells essentially. And then how do they actually train all of this? So initially they don't use these shells to train at all. They're just optimizing radiance with like your normal rendering formula. They're optimizing equal conditions as you do with SDFs. They're optimizing kernel smoothness. It's basically like a smoothness parameter S, and normals. So they're calculating like analytic normals, and they want their numerical gradients to like match the analytic gradients. So they're optimizing these 4 losses at the start and just optimizing your neural radiance field or like your SDF field as you may. And then after that, like midway through, they actually extract these shells, and then they optimize only in those shell regions, and they drop all the other conditions but the radiance ones. So they're only optimizing radiance at that point.
So how do they set the lambda?
Oh, it's probably just some hyperparameter search as well. Yeah. You mean these lambdas over here, right? Yeah. I think it's just some hyperparameter search probably. Yeah.
I didn't like it. So is S length per point?
Yeah, and they're outputting S as well.
Okay.
So your neural network outputs both the SDF value, the radiance value, and S. And then you use S like usually as you do in your equations to match your density there.
The erosion and the dilation is just for extracting the mesh?
Yeah, just for extract. Yeah, so they sample like F and S on like a regular grid, and then they do the erosion and dilation, and then they extract the mesh out of that. Okay.
how they decide the erosion and the dilation based on this?
That's a good question. There are some more details about it. To be honest, I don't remember exactly the details of the shell extraction, but they had some like arguments of like how they what the exact method is for the shell extraction. I didn't look into that much. Yeah, but if you want, you can find more about that in the paper for sure. Can I click this? I can't click this. Okay, so here are some results, I guess. Yeah, so I guess, like a side effect of this, the arguments are mainly about like speed up rendering, but as a side effect, they also get good reconstructions in like these fuzzy regions. I guess they have like how they decide how many points to sample in this like small shell. They can basically like increase the number because you're just sampling in this small shell, right? You can get like more denser samples in this small shell. So you get better reconstructions of like more fuzzy regions, and yeah, I guess just more details. Cool. Okay, thank you. All right, so here are actually rendering speeds, or how many frames per second they can render. I also include Gaussian splatting results. These are like concurrent works, but so you have instant NGP here. They only compared to like instant NGP and something else I don't remember anymore. But yeah, so I added like extra results from Gaussian splatting, and you can see it's actually like on the Mipner dataset, it's I think slightly slower still. Yeah, so it's 160 frames per second for their like 7K model in Gaussian splatting versus 36 frames per second for their model on the Mipner 360 dataset. All right.
What was the IMGP? Sorry, I was just checking the IMGP.
Yeah, I also checked it. I wanted to see if it's like consistent. It's kind of like in the same area, yeah. So for the Mipner 360 dataset, INGP is around 10 frames per second. And for Gaussian splatting, they also say it's around like 11 or 9, the base or percentage. Yeah. Yeah, so I guess those are generally the results. Can I go back to the results page? I'm sorry. Yeah, those are generally the results, and that's generally the whole paper. I think it's a very, to conclude, I think it's a very simple idea in general.
Yeah.
And it's kind of I don't mean to be mean, but it's kind of an obvious idea. But sometimes those obvious ideas are cool, right?
Yeah, I think we covered another paper a few weeks ago, like PLNer. They were trying to, well, it wasn't on news, but like it was on there, and they were trying to increase the precision per all the samples. And that just made the thin areas or fuzzy areas look better, but it didn't help with the speed. I think this is a very good follow-up to that. It's not a follow-up, but it's a good like confirmation.
Yeah. I think what really helps them a lot is like when you have like for the rendering speed specifically, when you have like a normal surface basically, then they use even just one sample for like array in this like thin region. They have like a bound for how wide your shell is, and then you can only just like use one sample, and then you can render using this one sample. I guess they're also here in the results specifically, they're showing like how many samples they need like per the sample count. So you can see how this is specifically why the frames per second is like so much. I'm sorry, so bad at this. Okay, yeah, this is specifically why the frames per second is like so much slower for Mipner 360, because you need way more samples per, right?
How does instant NGP do that? Is it just an not
Sorry?
Like with the instant NGP?
Yeah.
Like, I was wondering why they picked that as like a daily baseline compared with like mobile node and also using the magic.
Yeah, to be honest, I'm not sure. I think it was probably just more to elucidate the number of samples probably here.
I think they should have done with the new space, like the ones that use this.
Instant interface is like fast training, right?
That's true. Yeah, that's a good point. There was something else they were comparing to, but I don't remember at this point, to be honest. But I don't. They have mobile nerf here for the rendering speeds, but
For this paper, it is focused on faster renderings instead of
Mhm.
fast trainings.
Yeah.
Because you need to learn the shell extractions, which requires an SDF.
Mhm.
So I suppose they need to train a nerf style model first
Mhm.
to learn the geometries and determine the sampling space.
yeah, that's right. Yeah, they first train without this shell extraction at the start, and then only extract those shells to do the rendering.
I
Yeah.
think the applications that they're targeting doesn't really care about like training time.
Mhm.
Mm.
Yeah, for this part, it's only. I guess here they have more. Yeah, they have more baselines on the DTU and their synthetic and Shelly data sets.
Yeah, they have news.
They also have mobile nerf and vmesh. Oh,
Is
But this is only for photometric.
only for the what?
Like this table is only for photometric.
Yeah, only for. Oh, that's true. Yeah, oh, that's good. Yeah, I think that's good. There's ablations.
Is the PSNR value better or worse for this and 3D Gaussian?
Then 3D cautions. It's good.
Because they're like 3D Gaussians are also really good in modeling like this tin part.
Oh, they don't have PSR here. Wait, let's see. Okay, this will be a bit of navigation.
They're 32.
Oh, but I only have mobile nerf. Sorry, MIPNERF 360 results for the PSNR. Is there MIPNERF 360 here? Yeah. 24. Oh, but they're like. I guess here we just know 25 and 27.
Yeah.
And here it's either 24 or 29. I don't know how many indoors. It would be a bit hard to.
Okay. Weird.
Yeah.
Reporting. Yeah. Okay. Thank you.
All right. Yeah.
Okay. Well, I think that was all for today. Thanks to Anna and Yoon. So for next week, do we have any volunteers right now? Or if not, you can put your names into the sign-up sheet. Or message me on Slack or sharing. And we already have one sign up. We still need one more. Yeah. Okay. I'm gonna stop sharing and stop the recording.